Hi, welcome back. Non-determinism is an important feature used in abstract specifications because it allows some decisions to be made later at the appropriate time in development. In this lecture, we will present how the B method provides support for non-determinism. All the commands we have seen so far are deterministic. Therefore, the behavior of the commands was completely predictable, as there was just one thing to be done in a given situation. As a consequence, the state reached by an operation and the output values depended completely on the initial state and the input values. The B method allows the introduction of the non-determinism using the commands any, the non-deterministic assignment, choice, select, the operation preconditions, and in this lecture, we will also present the variable block definition using let. In the command NX, where Q, then T, and we have X being a new variable whose scope is within the command any. Q is a predicate and types X, and T is a machine command that means the body of the command. This command allows an arbitrary choice of a value to X that satisfies the predicate Q and then executes the command T based on this value. For example, in this command N, total will receive the product of its initial value by a random natural number greater than 0 called N. So we have the block N, where N belongs to natural 1, that means the set of natural numbers greater than 0, and then total receives the product of total by N. Another example demonstrates that we can use more than one variable. In this command, we assign sum to sum the sum of X and Y. So we have two variables, X and Y, where both of them are natural numbers, so X belongs to natural and Y belongs to natural, and then sum receives the sum of X and Y. One way to use any is to assign a random element from a set S to a variable XX. This command assigns to XS a random element of S. So we have any MM, where MM belongs to S, then assign to XX the value, the chosen value of MM. The B method, however, provides a specific assignment that achieves exactly the same result. By writing XX : S, we are assigning to XX a random element of S. For example, let us suppose we have a type player and a set squad that's a subset of player. The following set is the set containing all subsets of squad with exactly 11 elements. Therefore, this assignment non-deterministically chooses one of these subsets to assign to the variable team. The next command is choice. Choice S1 or S2 or as many commands as we wish, or Sn, and non-deterministically chooses one of the commands from S1 up to Sn to be executed. For example, the command choice A receiving 1, or A receiving 2, or A receiving 3, and we will randomly choose either 1, 2, or 3 to assign to the variable A. The commands within a choice may themselves be non-deterministic. For example, in this choice command, we can either have the execution of the N block or the assignment 0 to mark. But if the random choice is to execute the any, it will randomly choose a value between 1 and 10 to assign to the variable mark. The next command is select. It allows you to choose an option depending on whether it's enabled or not. It differs from choice because the choice allows the choice of any of the given commands, whilst the select allows the choice only among the enabled commands. Each option has a condition called guard that enables the option only if it's true in the current state. Therefore, we can see the select as a choice between the commands whose guards have a true value in that state. For example, let us suppose we have this select command. We have the select, if x is greater than 0, then we have x receiving x minus 1. Or when y is greater than 0, then y receives y minus 1. If we are in a state in which x and y are both greater than 0, then both guards are true. And this command behaves like the choice between x receiving x minus 1 or y receiving y minus 1. If, however, we are in a situation in which x is less than 0 and y is greater than 0, then only one of the guards is true, the second one. And we actually have the execution of the command y receiving y minus 1. We can also have the other way around, in which y is less than 0 and x is greater than 0. And in this case, the first guard is true, and we have the execution of x receiving x minus 1. Finally, we can have the situation in which both variables x and y are less than 0. And in this situation, we have an unfeasible command. That's why we also have the choice of including an else statement in the select command. So I suppose we have else skip in this command select. And in this case, if both variables are less than 0, then this command simply skips. Let's now show a final example on the select command. Let's consider a set of members from a sports club and subsets tennis P, croquet P, and squash P that contains the members of the club that play tennis, croquet, or squash. There's also the enumerated type status that has 4 elements: tennis, croquet, squash, and non. And now let's suppose we want to create an operation that receives a member and returns tennis if he is in tennis P, returns croquet if he belongs to croquet P, and returns squash if he is in squash P, and finally returns non otherwise. If the member is in more than one set, then any of the possibilities can be returned. This can be implemented with this operation. Sports MM is an operation that returns the corresponding value via the variable RR and receives a member MM and then executes this select command. If M belongs to tennis P, then RR receives tennis. When M belongs to croquet P, then it assigns croquet to RR. When M belongs to squash P, then it assigns squash to RR. Else, it assigns non to RR. So you can see that if a given member MM belongs to more than one of these sets, tennis P, croquet P, and squash P, then this command will non-deterministically assign tennis, croquet, or squash to RR. We can actually animate this machine, the machine sports club, in Pro B. So we have here the abstract specification of the machine sports club. We have 2 sets, the set name and the set status, with tennis, croquet, squash, and non in it. And we have 4 variables: the set of members, which is a subset of name, and 3 subsets of the set of members: the tennis players, the croquet players, and the squash players. All 4 sets are initialized with the empty set. So we have the assignment of the empty set to these 4 sets. So here we have 3 operations. We have the operation add member, which receives a name and includes this name in the set of members. We have the operation add sport, which receives a member and a status. And if that status is tennis, we use here the command case. So in the case of SS being the value tennis, we add this member to the set of tennis players. Or if it's croquet, we add this member to the set of croquet players. Or if it is squash, we add this member to the set of squash players. And finally, if it's different, if SS is different from tennis, croquet, and squash, we simply. And finally, we have the operation we have just seen. So the operation sports receives a member, and then we have the select command that we have already discussed. So here we can animate this machine, initializing, and let's add, for example, name 1, 2, 3, 4, and 5. And now we have here in the left that the members contains all 5 names, and notice that I can invoke add member as many times as I wish, simply because I didn't forbid adding members that were already members. That's not important here. And finally, we can add sports to these members. We can say that, for example, name 1 plays tennis, and we can say that name 1 also plays croquet, and let's say name 4 plays tennis also. Here, see that the tennis players are name 1 and name 4, and we have that name 1 is a croquet player. And finally, if I ask what sports name 1 does, I can actually receive 2 outputs. I can either get tennis or croquet. So there is a random choice of this machine if the output is going to be tennis or croquet. So by simply invoke sports, with the argument being name 1, I have 2 possible outputs, and that characterizes non-determinism. If we go to Atelier B, we can actually see that this machine has already been proved consistent. So as we discussed in the previous lectures, all the statements here in this machine are consistent among each other. Our next command is the operation precondition, which we in fact have already presented in the previous lectures. This command introduces non-determinism because the call of the operation does not mean that it will be executed correctly. This will only happen if the precondition is satisfied. Otherwise, the behavior of the operation is unpredictable. For example, the command pre-x greater than 0, then x receiving y divided by x, is only correctly executed if x is greater than 0. It's important to notice that ProB has a blocking approach of preconditions. Operations can only be executed when the preconditions are true. Let us go back to our sports club example. So going back to our example, let us reinitialize our machine. So we reopen the sports club, and now we go back to our initial state here. So let's initialize my machine. And you can see that all I can do here is to add members, because the other operations like, for example, add sport or asking the sports of a given member, they require members to have elements in it. So that cannot be invoked if you do not have members. So that's why ProB has a blocking view of preconditions and actually does not provide in a simple manner the invocation of these operations. We can, however, using ProB, try to force the invocation of an operation outside this precondition. Or we can actually execute an operation. Let's say I want to add a sport to a given member, and as we know, we don't have members, but let's say I want to say that I want to add tennis to the name 1, and if I execute this operation, we actually get an error here saying that we have broken the precondition and it's not possible to execute that operation. That's why we say that ProB has a blocking view of preconditions. Let's go back to our lecture now. Before moving to a non-deterministic example, let us present a command that, despite being a deterministic command, has not yet been presented. The command let, like in this example, let it be it equals e in S, declares a local variable, in this case it, whose initial value is defined by the expression e, and executes S with it in scope. It's equivalent to the command nit, where it equals e, then S. Now, let us present our final example, which is a model of a simple and funny jukebox. The jukebox contains a set track, which is a set of possible musics, and stores the musics to be played and the number of credits. This machine has 4 operations. We can purchase credits up to the machine limit. We can add the music to the set of musics that the jukebox should play. We can randomly choose a music from the set of musics that the jukebox should play. And we can penalize the user for mistreating the jukebox. This will either cause a loss of 1 credit or 1 music, if any. By way of illustration, let us suppose that the jukebox has a limit of 4 credits. And now the client pays 1 credit. And now let's suppose we also pay 10 credits. Notice that the credits stayed at the limit 4. Now let's select track 1. And notice that the set of music now contains track 1 and the credit is 3. Let us now select the track 1 again. And notice that the credit is decreased, but the set of music remains unchanged. So the set of music is still with 1 element only, track 1, and the credit has decremented to 2. Now let us select the track 2, and notice that the set of music is track 1 and track 2, and the credit remains 2. That's because this machine, every time we select a track, it can either take the credit of the amount we have or not. It randomly chooses to do so. Let us now select track 3. Now the set of music contains 3 elements, track 1, 2, and 3, and this time the credit has been decremented by 1, so it's 1 now. Finally, let us select the track 4, and the set of music becomes the set containing the elements track 1, 2, 3, and 4, and the credit now is 0. Let's now suppose we call the operation play, and the machine, the jukebox, randomly choose 1 music, in this case, in this example, track 2, and the set of music becomes the set containing the elements only 1, 3, and 4, and the credit remains 0. Now, let's suppose the user has done something wrong. We play penalty, so we invoke the operation penalty, which in this case can only remove 1 music because there is no credit to be removed. So it randomly chooses 1 music to be removed from the set of musics, and in this example we have that the final set is track 1 and 4. Let us now pay 1 credit, and notice that the credit becomes 1 now. And let's once again invoke the operation penalty. And now this operation can either decrease the credit, resulting in a credit of 0, or it can randomly choose 1 music from the set of musics to be removed from this set. So the definition of our machine, the machine jukebox, contains a set called track, and we actually have a limit, which is a constant, that is a natural number greater than 0. This machine has 2 variables, credit, that stores the amount of credit we have, and play set, that stores the music that the machine should play. So credit is a natural number, but this credit has a limit, so it must be less or equal than the constant limit. And our play set is a subset of the tracks, the possible tracks. We initialize the credits with 0 and the play set with the empty set. As I said, we can now pay a credit. So we receive a natural number greater than 0, but the variable credit will receive the value, the minimum value between the current credits plus CC and the limit. That means that if the amount of money that the user gives summed with the credit, the current credit, goes above the limit, then we stay at the limit. We will see that later in the animation. Now we can select a music, and to select a music, a given track, so you select a track, we must have credits. The user can only invoke that operation if credit is greater than 0. And here is the choice I mentioned. So this machine randomly chooses either to simply add that music to the set of musics, or to add that music but also to remove one credit from the credits the user have. Next, we have the play operation, and it can only be invoked if the set of musics to be played is not empty, and it chooses any TR where TR comes from the play set and assigns TR to the output TT, and also, of course, removes that track from the play set. Finally, we have the penalty operation, and if the user has credits, so if credit is greater than 0, then it can remove one credit from the current value of credit, and when the playset is not empty, then it chooses any music PP that comes from the playset and remove that music from the playset. Otherwise, if there is no credit, so if credit is equal 0 or less than 0, or it actually cannot be less than 0, so if it's 0, or if the playset is empty, then this operation simply skips. Notice that if we do have credit, so if credit is greater than 0, and if we do have music to be played in the playset, so if the playset is different from the empty set, this machine will randomly choose to either take one from the credits or remove one music from the playset. And if it does choose to remove one music from the playset, then it randomly choose which music is going to be removed. So let us now do exactly what we had in this animation, in our previous animation. So let's suppose we have a limit of 4, so we set up constant to be limit 4, and we initialize the machine, and let's suppose we pay 1 credit. And now notice that we have a credit of 1 and the limit of 4, and the playset is empty. So let us now pay 10. So if we pay 10, notice that although the sum of 10 with 1 becomes 11, we have 11, we stick the credit to its limit, so credit becomes 4, not 11. Now let's select track 1, and notice that this time the credit has been decreased by 1. And now let's select track 1 again, and again notice that the playset remains unchanged because we simply add track 1 again to the set, and that the credit has been reduced to 2. Now let's select track 2, but let's notice here that we have 2 options of selecting track 2 here and selecting track 2 here. And I know, because I have already animated this machine, that this one corresponds to the random choice of not removing the credit. So let's execute this one here, and notice that here I added track 2 to the set, but I didn't remove the credit from its current value. And now let's select track 3, and let's select track 4. Now I have 4 tracks in my set. I have no credits at all, and the limit is a constant, so it remains 4. So let us now play a track 2. So notice that play has 4 options here. So by simply invoking play, you can have 4 outputs. And as I said, that characterizes non-determinism in Probe. So let's suppose we invoke play and we get track 2 as output, and notice that the track 2 has been removed from the set and the credit remains 0. And now let's call penalty. Notice here that penalty has 3 options, but all of them do not change the credit simply because we don't have the credit. So we don't have a random choice of either removing a credit or removing a music from the playset. But we do have a choice, a random choice of which music is going to be removed from the playset. So let's suppose we do remove track 3, so we choose this one here. So track 3 is removed, randomly chosen to be removed from the playset. And let's suppose now I pay something, and now I have a credit of 1 and 2 music in the playset. And now if I do invoke penalty, I do now have the choice of either removing a music from the playset or removing a credit. So here I remove the credit, and here I will remove a music. And if the random choice is to remove a music, I can either remove track 1 or track 4. So let's suppose here that we do remove the credit. So now we have the credit removed. That finishes our animation in the Pro B. And now if we go to Atelier B, we can type check the jukebox, we can generate the POs, and let's invoke the automatic prover. And we notice that here one of the proof obligations has not yet been discharged, and that's regarding the well-definedness of invoking the mean operation. But as I said, that's not the focus of this lecture. We have extra material that will discuss exactly all the proof obligations of our examples in this course. So that's why I would say we completed our example of the jukebox. And that's all for this lecture. See you in the next one. Bye.